So we're going to take a look at something that we might want to interpolate. So census data used to get, God help us all, stupid long form cancellation. Anyway, sorry. My mom worked at StatsCan. She was a director in Stats Canada. And when the government decided, oh, 5 people complained about the long form census, we should cancel it. And if you're seeing some of the knock-on effects for social studies that are happening after that cancellation, the replacement of the National Health Service, it's a frickin' disaster. It's just, it's bad science. Anyway, don't get me started. All right, too late. Anyway, the census figures used to be a reliable source of census information for our country. We'll see how we go forward with that. But in the meantime, let me just open up some data here. And there we go. So this is a kind of a gross way, but it's a manual way to enter in some census data every 10 years back in the 1800s. And we can plot that and see how our population has burgeoned up to 2006. And we're going to put a close. Oh, I did. Oh, I better put a plot. So actually, this is a good point. My data here is now a 2-column vector. 2-column matrix. 2-column matrix. How would I go about plotting this as data? Straight out of your assignment number 1. Any suggestions? I'm going to have a plot. What do I use for my x values? Yeah. Exactly. We need index. So we want the first column. That's where our x's are. So how do I get all the elements of the first column? What's syntax? P. What's the one-letter way to do this? All the rows. Yeah, all the rows is a colon, comma 1. And then same thing for the y. I want all the rows but the second column. And I want to plot those as dots. So it's a little more complicated than x and y, but that's fine. It's well within our abilities here. And that will generate our graph. Poof, there we go. So, hello, baby boom, post-Second World War. It's pretty obvious on this graph what's going on there. So, we got our data. But say the classic question would be, how can we estimate, say, the population in a year that's not a census year, so between 1901 and 1911? Well, that's where an interpolant would make sense. We know this, we have faith that this data is accurate, at least as accurate as any census data is. So what we do not want to fit a curve through or approximately near these points. We actually want to go through these points. And so here we'd actually do our spline. We'd say PP is a spline. Our data for the x's, exactly the same thing we use for our plot. Data for the y's, exactly what we use for our plot. And that's all we need. And then we're going to need some linearly spaced numbers for our graph. We went from 1851 up to 2006. And then we would have evaluate our PP generated from the spline at those XX values and plot them. So those are the kinds of steps you'll be expected to start to work through. First line, generate the spline. Spline, x and y, there's my data. Perfect. Generate the coefficients. Now it's going to be like 80 sets of coefficients. Then generate some linearly spaced x's that I can use for plotting. Pass those to the evaluator with my spline, and presto, doof, we get our graph. I'm going to put the hold on here, which I forgot. There we go. Lovely. So yeah, now we could actually ask in a reasonable way, hey, what was the population in 1924? And have a reasonable estimate for that. Just for contrast, we'll do the p-chip one as well. And I'll show you that with the 3-input argument one, p-chip. We can say, OK, I'm going to build a p-chip, but I don't really care about the coefficients. So let's just evaluate that at my x's, which are the first column in p, at my y's, which is the second column in p, and at the xx values. That's where I want to actually get my graph. And then we use the same x's in our plot, because those are the same no matter what. But then we use our chip values. Oops, y chip. Oh, y p-chip. There we go. Lovely. And again, you get almost the same graph. I'll show the code for a second, then we'll go take a look at the graph in detail. Any issues running it, getting it to run? Fantastic. All right. Question? No. OK. All right. Then let's take a quick look at the graph and recognize, just like the last one, even though there's some guarantees of the p-chip that it's going to be monotone increasing, the biggest differences we see are tiny in comparison. Like in 1948, when this big change is going on, 1946, there's a tiny difference in population. These are tens of millions, but it's a tiny fraction of a difference there. So for without any other information about which graph is better based on intermediate studies, both of these are providing pretty reasonable and intuitive estimates of the population in between census dates. So yeah, that's how we use these things, pretty much. Last little comment is basically that, oh, right. I will kick it up one notch. Here's where we actually get into the coefficients. What if I wanted to know how quickly the rate of population growth was, or what the rate of population growth was in 1914? On this graph, the rate of change is what altogether? What does it look like? Slope. That was not anywhere near as unanimous as people graduating from 171 should have been. What am I looking for in this graph? Thank you. How do I get a slope? Yeah. You can differentiate. Right. So we can differentiate our function. Now here's where, especially for the roller coaster folks, this is where we actually have to break into that PP matrix. We would need to figure out which interval we're on. Well, we can figure that out pretty easily. If I look at my PP breaks, let's go down to here. 1914 is after, it's in the first interval, second, third, fourth, fifth, sixth. It'll be in the seventh interval. So if I look at my coefficients and spell it right, let's actually do it this way. I can look at the seventh row of coefficients by saying the seventh row, all the columns. Those would be my coefficients for the polynomial. Now if I wanted to get the derivative, this isn't actually a polynomial, but it has all the information I need, how would I differentiate that? Yeah. Perfect. Multiply these elements by 3 and so on. So I'm going to grab these. I'll just show you this on paper. Whoop, that's not what I meant to do. Just you guys. Because you're absolutely right. The process of generating a derivative comes from interpreting this. We have 0.003 times 10 to the 6th x minus, it was 1911, cubed, plus minus 0.0056 times 10 to the 6 millions, x minus 1911, which is the breakpoint before that, squared, plus. That's our function. And so if you want the rate of change, take the derivative. Now you can write it out. You know that f prime will be 3 times that coefficient there times x minus 1911 squared minus 2 times this guy, because you bring the coefficient down, etc., 0.0056 x minus 1911. And you just do that all the way through. So getting a new polynomial is actually super easy. In fact, let's do that last step. If I wanted that polynomial, I would just read off the coefficients and multiply the ones I had to start with by 3, by 2, by 1, and the last one's a constant coefficient. It would actually turn into 0. In fact, I'd stop here. That would be the x squared coefficient, that would be the x coefficient, that would be the constant coefficient. So there's going to be a systematic way that you can work from the coefficient matrix, grab a row, those are the coefficients of one function, take the derivative by manipulating those numbers and getting a new function out of it.